Hello everyone and welcome back to another minute concept, this time about physics, and rather this is an in-depth concept now. So today we're going to be proving work and energy relations. And what are these? According to, well, the books, we know that work is equal to delta KE, or the change in kinetic energy, as well as the negative change in potential energy. But we want to actually prove this. And how do we prove this? We're going to be able to prove this using the equations for kinetic energy and potential. Now, in the other video that I made, I think one or two videos back, we were able to discuss the conservation of mechanical energy. And from there, we can actually prove as well another work energy relation. And we can do that by proving that the change in PE, or the negative change in PE, is equal to the change in KE. So without further ado, let's get to solving and proving the first equation. So we know that W, or work, is supposed to equal the change in KE. Hold on, let me get rid of all of the other ones first, since they're kind of spoiler alerts. So we know that we have to prove this. Now, where do we start? We know that work is equal to FD cosine theta. So work, hold on, let's use a different pen throughout our derivation. Let's use blue. We know that work is equal to FD cosine theta. Now, assuming that cosine theta is maximized, let's just use cosine 0, which will equal 1. So we're just going to get rid of this now. So from here, we can also say that work is equal to mass times acceleration times displacement, or MAD. Work is MAD. Now, we also know that KE is equal to 1/2 mv squared, and to describe delta KE, it would be final minus initial, KE final minus initial, which is also equal to 1/2 mv f squared minus 1/2 mv I squared. So from here, we can try to equate the two, though obviously it wouldn't really make sense yet. If we just go ahead and do this, and then we're going to equate it to 1/2 mvf squared minus 1/2 mvi squared, it kind of doesn't make sense, because one, there's no d here in the other equation. So how do we get that? Alright, so the answer to that question is quite, I would say intuitive, but at the same time, very logical. Okay, so this equation for work, FD, this actually describes work on an average, I'd say, or in the sense that it's not instantaneous or changing, because work is actually described as the area under the curve of a force times displacement. And if we're going to get the area under a curve, we need to use integral calculus. Now, we don't have that, so we're working with constant force. And with constant force, we have constant acceleration. So constant force is equal to constant acceleration. That means if we have constant acceleration, we have uniform acceleration, and we can use uniformly accelerated motion to describe our object. Now, using uniformly accelerated motion, how do we get to any of this here? We have to look for an equation that has acceleration, that has Vf and Vi, as well as displacement. So if we're going to look through our equations, we can actually find that the equation that satisfies these conditions is equation number 4, which I'll write in my yellow pen. So UAM equation 4. And this is equal to the initial velocity squared is equal to the final velocity squared plus 2 times acceleration times delta x. However, delta x is also equal to displacement. Delta x is equal to displacement. So this can also be written as just d, 2ad. So let's use this now, and let's derive certain values. So if we're going to flip this equation around, we'll put this on the right side. Hold on, just like that. And we're going to put it here we can see that we're getting somewhere in the sense that we actually have two of the variables that we need on the left side. So what does that mean? We just need to derive the value of AD, since that brings us one step closer to getting the equivalent of MAD. So without further ado, let's try deriving from there. I put it in yellow pen so that we can show that there's a distinction from this. This is our end result, okay? This is where we need to get to. So let's box that just so that it's separate. So from here, let's start deriving. We want to isolate 2AD, so we're going to subtract VF squared from both sides. So that will give us VI squared minus VF squared. Now, after this, we want to get AD alone, so we're going to get both sides divided by 2. So VI squared minus VF squared divided by 2. Since they share the same denominator, we can split the fraction. AD is equal to VI squared over 2 minus VF squared over 2. Now, we're looking for MAD. We're clearly lacking an M. So what do? Well, it couldn't get any simpler rather than just multiplying M to both sides. So M times AD is equal to everything on the right side times M. And this will give us a final answer of MAD is equal to MVI squared minus VF squared over 2. Oh, hold on. We made a mistake here, sorry. This should be VF. We flipped our values when we were reorganizing our solution earlier. So this should be, okay, should be F, I, F, I, F, I, F, and I. Apologies for that, but for those who spotted it, that's a good job. Okay, so continuing, we get MVI squared. Okay, so now we can just separate these two, these fractions from their coefficient, which should be 1/2. So that's MAD is equal to 1/2 MVF squared minus 1/2 MVI squared, which is equivalent to the statement we have on the top. And thus, we can say that since this is equal to work, and this is equal to work, and this is equal to delta KE, work and delta KE are therefore equal. So that's the proof for work is equal to the change in kinetic energy. So now, let's go to the next one. Let's prove our next problem, which is work should be equal to the change in, or the negative change rather, in potential energy. Now, going back to our formulas, let's just use the bare bone definition of work, which is MAD again, just as I did earlier, and PE is equal to mgh, and delta PE is again described as final minus initial, so that's mgh1 of 2 I mean rather, or mghf minus mghi. Okay, so now let's write our equation in this format. We want to prove that work, or MAD rather, is equal to mghf minus mghi. Now, our acceleration here is actually given. Our acceleration is g. So we don't have to worry about these two being different. While they're different letters, clearly, g is still a value for acceleration. So we're just going to disregard that difference. From the right side of the equation, we can factor out mg. Now, mg, for those who know or remember from the past videos, is equal to the force of gravity. Well, I was supposed to explain that, but I accidentally spoiled it for you guys. That's mg. So the force of gravity, we can simplify that. Times the final height minus the initial height. Now this is all equal to mad again. When we're talking about the differences in height or position, we're also talking about displacement. So from here, we'll just expand FG again. We'll go back to mg, and then we're going to multiply it to total displacement, which is also equal to MAD. Now the question is, why is it that the change in potential energy, or the negative change in potential energy, is equal to work? Now the answer to that is because work done by gravity is negative. And the work done by gravity is negative because it's an opposing force, right? And normally when, for example, when an object is thrown upwards, it's going to oppose. And the only time it's ever positive is when it's going to be going downward. Now, if that's the case, then let's reason it like this. When an object is going up, okay, so let's say that this ball is going up. Okay, so that's going up now, right? When it goes up, its potential energy decreases. And there is negative work done. Now, when an object is going down, its potential energy... Oh wait, sorry, rather, when an object is going up, its potential energy increases. Now, when an object is going down, its potential energy decreases and it turns into kinetic, and there is going to be positive work done. So, using this intuitive explanation, we can say that the relation is inverse sines, or rather, it's like work is equal to negative work is equal to the positive change in PE when it's going up, and simplifying this into like the other version, it will become work is equal to negative PE when it's going down. So you can actually write these two equations just alternately, depending of course on your situation, and they will work just fine. So it's more about situational analysis for this one, rather than just having straight mathematical analysis like the last proof. So I hope this was clear. Basically, the change in potential energy is what's going to dictate the sign of our work, and vice versa. And that's because of the concept of mechanical energy conversion. Now, I said earlier that we can prove that delta PE is equal to negative KE, or negative delta KE, or negative delta PE is equal to the delta KE. So let's try doing that now. So we want to prove that delta PE, or negative delta, is equal to delta KE. And we're going to invoke the conservation of mechanical energy law. So the conservation of mechanical energy, conservation of TME, which is called TME, states that PEI plus KEI, or initial potential energy plus initial kinetic energy, should be equal to the final potential energy plus the final kinetic energy. Now, we want to we want to show their relation together, right? So we want to see that delta PE is equal to delta KE. In order to do that, we need to solve for them in one term. So we're going to define first our deltas. Our deltas are described as delta PE is PEF minus PEI. And we also define our delta KE as KEF minus KEI. And for those who are wondering, whenever there's a delta, it is always final minus initial. Okay, so we have this now. Where do we go from here? Let's try to solve for this relation in terms of PE. So now I'm going to use a different pen to show that we're already in the problem solving part. Well, not really in the problem solving, but rather the derivation portion. So we want to show that these are equal. We need to show that we have to write delta KE in terms of PE. So what we're going to do is we're going to rewrite this delta KE is equal to KEF minus KEI. Now before that, let's try to derive KEF. Alright, let's try to derive KEF. Because I think that KEF, when it's defined in terms of PE as well, we can actually cancel out KEI. So let's test that out. Let's see if that's true. We can derive KEF from this law right here. So if we're going to isolate KEF, we'll get PE initial plus KE initial minus PE final is equal to KE final. So let's plug this in to our working equation. We'll get initial potential energy plus initial kinetic energy minus potential energy final minus initial kinetic energy. So these two will cancel out. Now we're left with delta KE to be defined as initial potential energy minus the final potential energy. Now we're getting somewhere. We can see that these two are so close together. Let's use a different pen. This statement right here and this statement are so close to one another. What's their difference? They differ because one of them is a negative version of the other one. Now let's put them side by side. Let's write this in our purple pen now because we're nearing the end. Is equal to PEI minus PEF. Now, we're also trying to show that they're related to one another, so let's equate them. Let's put PEF minus PEI. And this should be equal to delta PE. If you notice, our value here for PEF minus PEI, this is actually a negative version of our delta KE. So, in that sense, we also have to multiply negative to our delta PE. So if we're going to make a unified version of this now in one line, we're actually going to get KE is equal to PEI minus PEF, and this is equal to negative PEF plus PEI, which is also written as PEI minus PEF, and this is equal to the negative change in potential energy. So that is how you solve for the conservation of mechanical energy, and we also prove that delta KE is equal to the negative delta PE. And this makes sense. How do we know this? This is because in different situations, our change in energy is going to be different. So for example, take this ramp. Okay, let's say that like in some perfect universe, this ball can make it all the way across. So there's a ball that's going down. When an object is going down, like I said earlier, its PE is decreasing. This is negative change in PE. And its KE is increasing. So that's positive KE. Now these two should always add up to TME. So regardless, this will always equal the same. So because that negative delta PE, as we already said, is equal to just delta KE. Now, for example, let's say that it reaches the bottom and it's going up now. The ball is going up the ramp. Now, PE is increasing and its delta is positive. Positive PE. Now, on the other end, actually, let's zoom in here. On the other end of it, KE is decreasing because it's losing its speed, it's going up, it's becoming more potential. So it has a negative delta. And this is now true because this equation right here can be written as well as delta PE is equal to negative change in KE as seen in these situations. So that is how you prove those three work energy relations. So thank you everyone for watching, and I hope you guys learned a lot from this in-depth concept. Proving is a hard task for someone who doesn't know where to start. So when you're going to prove, I suggest that you start somewhere that is the most basic form. That's why we always break down our derived values such as F into MA. And we also break down our values of Ke into its versions of 1 half mv squared. We always have to break it down to the most basic points because that's where we can find their alignments. And of course, think outside the box. Not everything in physics is solved by formulas. You actually can you can logic your way through some of them. So when you hit a wall, let's say in an exam you're asked to prove for this, try to think outside of the box. And though it might be a daunting task, I'm sure that you guys can try to find a way for it as long as you practice. So thank you everyone, and I hope you guys learned something again from this in-depth concept about proving the work-energy relations. Thank you everyone, and goodbye!